this is how far we had gotten in our analysis. We had run the regression model using the GLM function, and I typed model 1 to call the function, the results of the function, and this is what the output looks like. So you can see that R gives you the output in the form of the coefficients. So the intercept is negative 1.6. The coefficient for the exclamation attribute is 8.2, and the coefficient for the spam data is 19.01. Now that I've actually gotten the results of my regression analysis, I can move this to Excel to conduct the rest of my analysis. So I'm going to move back to my Excel file, which was called spam Excel. This was the original data set that I was working on, and I've created a separate tab where I added only the values for my training set, so it goes up to only row number 72. And here I've sort of created a template that I'm going to use for the remaining part of the analysis. Now, as you can see that I've already created cells for B0, B1, and B2. These are just values that I took from my regression output in R. The intercept was negative 1.64. The exclamation coefficient was 8.2, and spam data coefficient was 19.01. And that's exactly what I've added up here. You might get slightly different numbers in the second or third decimal places, but that's acceptable because those values are not going to be far from each other. So remember that the regression equation that I have is not actually for the probability of an email being spam or not. In fact, this regression equation is for the logit. So if I go back to my equation here, the regression results that I've received are for the logarithm, the natural logarithm of the odds. So I have to first calculate these odds and then reverse engineer to calculate the probability, which is what we're going to do next. So the logit function essentially is going to be what you have in this results here. So we're going to use these three values here to calculate the logit. Let's use the results from our regression analysis, which I've copied over here from my R output. These are the only three numbers that I need to use for now. I'm going to use them and the regression equation that I drew over here to calculate the value of the logit. So the logit is equal to beta 0 plus beta 1 multiplied by the value of x1 plus beta 2 multiplied by the value of x2. Now, because the values of the betas remain constant, I'm going to put absolute cell references. Now, because the values of the betas remain constant and I want to drag this formula down and copy it all for the rows, I'm going to put absolute cell references here for J1, J2, and J3. You can do this by using the function F4. You just have to put your cursor in the middle of these and press F4, and that'll add the dollar signs, and that fixes the value once you copy this formula down. So for example, here you can see that the values of x1 and x2 changed, but the values of J1, J2, and J3 remained the same. So I'm going to copy it for all my values here. And now I've calculated the logit. From the logit, I'm going to calculate the value of the probability. So right now what I have is the natural log of the odds. So I want to convert this back to the probability so that I can then use this probability to classify my emails as spam or not spam. In order to convert my logit into a probability value, I'm going to use the formula which is given in the lecture slides. This is specifically slide number 42, where the formula is given this way. The probability is equal to 1 divided by 1 plus exponent to the power of negative logit. So that's what we're going to do, is we're going to use this same formula, 1 divided by 1 plus exponents function is exp in Excel, and that to the power negative logit, which is given in cell E3. And I close this, and now I can just copy this down to get the value of my probabilities. What you'll notice is that none of these probabilities are greater than 1 or less than 0, which is what we exactly wanted. And now, using a rule, we're going to convert it into a binary variable. The rule that I want to use is that if the probability is greater than 0.6, then I want the class to be 1, otherwise 0. So you can change this rule. This is up to the researcher or the data scientist who's working on this. If you think a probability of 0.5 is sufficient for you to determine the class as 1, you can change it from 0.6 to 0.5, or you can even increase it if you want to be more sure about the class. So if I press enter here and I drag this down, I now have my binary predicted variables. Now you'll see that the predicted y class is 1 and the actual y class is also 1. However, there's one case where the predicted is 0 and the actual was 1. So in order to test how well our model performed, we're going to create this matrix where in the columns are the predicted values and in the rows are the sum of the actual values. So essentially this cell in green, K6, represents the values which were predicted to be 1 and they were actually 1. L6 represents the values which were predicted to be 0 but in actuality they're 1. And K7 represents the cells which were predicted to be 1 but were actually 0. And finally L7 is the values which were predicted to be 0 and they were actually 0. So I've labeled these two cells in green because these are the accurate results, and these two cells in orange because these are the incorrect or the mispredictions. So let's use the COUNTIFs function to count this for us. We want Excel to check how many of these values in the cells D3 to D72 are equal to 1. And we also want Excel to check how many in these cells G3 to G72 are equal to 1. Okay, so out of the 70 values, 38 of them were correctly predicted to be 1. Let's copy this function and paste it here, but instead I want the cell references to remain the same. So I'm going to change that. G and G. If you don't want to change again and again, you can just press F4 and make these constant references. Now, however, in cell L6, we want to calculate how many values were actually 1, but the model predicted them to be 0. So I'll convert this last criteria to 0, and looks like there were 6 values but that were actually 1, but the model predicted them to be 0. The same way, let's copy this formula and switch around the numbers to represent predicted and actual. And here it's predicted 0 and actual is also 0. Okay, so now I have all my numbers. The sum of these should actually sum to 70, and that's what I'm checking for now. Yep, that's correct. Now I can determine the accuracy rate, which is how many values were correctly predicted out of the total, which is represented by the cells in green. That divided by the total tells you that 89% of the values were accurately predicted to be the same class as they were in the actual data. We can also find out the error rate for each class. So that's going to be equal to the error in class 1 divided by the total number of values in class 1, and the errors in class 2 divided by the total number of values in class 2. So the error rate for class 2, which is class 0 essentially, is lower than the class 1, which means that we are incorrectly predicting very few values to be spam, and we're predicting more values to not be spam, which means that we're actually letting more spam emails go into the inbox based on this data set that we have. Now, with the help of this example, you were able to clearly apply regression model in a logistic format where we transformed our y variable into the natural log of the odds, and then we reverse engineered to get the probabilities and get the predicted class that we wanted. In the middle, we used R to run the actual regression analysis for us, and that was just briefly, but it was extremely helpful because otherwise we would have spent a lot of time running this logistic regression.